All right, if something is amphoteric, that means it can act as either an acid or a base. And there's quite a few things out there that can do this. And one of those is your good buddy water, right? So if I take sulfuric acid, H2SO4, and I put it in water, right, water is going to act as a base. It's going to be the proton acceptor, right? It's going to become hydronium, and then you get your hydrogen sulfate over here. When I put ammonia, NH3, into water, water acts as an acid, all right? It's the proton donor. So here, it's the proton acceptor. Here, it's a proton donor, all right? It's an acid or a base, kind of depending on the situation. So get ready for this, though. So if it can act as an acid or base, it can react with itself. That's really trippy. So water can actually react with itself. One water molecule is a proton donor. Another water molecule will act as the proton acceptor, and it'll create hydronium and hydroxide. This is called the autoionization of water. So it'll just do this, and it's an equilibrium thing, right? Obviously, these will come back together and make water. Before I even click on it, do you think this equilibrium lies way to the right or way to the left? Hopefully, you're thinking way to the left, and you would be right. Or, sorry, you would be correct. No, dun dun dun. Okay. Anywho, you could write the equilibrium constant expression, right? Products over reactants, the coefficients become exponents, solids and liquids don't go in, right? So you'd get this, KEQ equals hydronium concentration times hydroxide concentration. This is such a special equilibrium constant that it's given its own name. We call it KW. All right, it's the autoionization constant of water. And also so important that you should actually memorize the value of KW. So KW at 25 degrees Celsius is 1 times 10 to the minus 14. All right, so yeah, that's a very small number. The equilibrium definitely lies way on the left. All right, so not a lot of water if you go get a glass in your kitchen, is going to be, hydronium hydroxide, but there's a tiny, tiny amount of these in there. Yes. When we have an acid, right, if we put something in there that's going to increase this, right, this times this is always the same number, right? This is a constant, so the hydronium goes up, the hydroxide goes down, all right? But acidic solutions are going to have more hydronium than hydroxide, and basic solutions, are going to have more hydroxide than hydronium. If the hydroxide and hydronium are equal to each other, that is exactly neutral. Let's get into pH. So the pH, the actual definition of pH, you may have heard about pH, like swimming pool, we've got to adjust the pH, or like this, that, and the other thing. It's how we measure how acidic or how basic something is. We use this pH scale. And the actual definition of it is, it's the negative base 10 logarithm of the hydronium ion concentration. All right, if you haven't done logs in math, don't worry about it at all. I can explain it to you in class if you want. But really, for you guys, it's a button on your calculator. All right, so if you know the hydronium ion concentration, all you have to do is put that in your calculator and hit your log button. Boop. And it's going to give you your pH. You may have to flip the sign in your head. That's usually what I do. Or you can actually just put this whole thing into your calculator the way it is, and you'll get your pH. All right, so in pure water, right, KW is the hydronium concentration times hydroxide concentration equals 1 times 10 to the minus 14. These are the same. Like for every hydronium you get a hydroxide. So in pure water, these are equal to each other. Right? And if I wanted to calculate the hydronium ion concentration, I would just take the square root of 1 times 10 to the minus 14, and that is 1 times 10 to the minus 7. So if I want to get the pH of pure water, I need to take the negative log of the hydronium ion concentration. So the negative log of 1 times 10 to the minus 7 is 7. Right? Acids are going to have higher hydronium concentration than pure water. So in an acid, I might have 1 times 10 to the minus 3. Right, 1 times 10 to the minus 3 is higher concentration than 1 times 10 to the minus 7. So 1 times 10 to the minus 3, the negative log of that is 3. 1 times 10 to the minus 2, negative log of that is 2. So now hopefully you're getting an instinct as to what that log's doing. If I have a base, it's going to have a lower concentration. So maybe I'll have 1 times 10 to the minus 9 moles per liter of hydronium. And the negative log of that would be 9. Right? Or 1 times 10 to the minus 10. So the negative log of that would be 10. So pH would be greater than 7. All right, so just remember, when you have an acidic solution, the pH is less than 7. If you have a basic solution, the pH is greater than 7. Think of it like a pyramid, right? What's the big part of a pyramid, right? The base. The pH scale runs from 0 to 14. The big numbers are base. Big is base. Base is big. All right, so the bigger pH values. But right smack in the middle there, right at 7, that's neutral. All right, that's when your H plus and OH minus concentrations are equal to each other. All right, so here's just a bunch of pH values for a lot of things. So stomach juices are on pH 1, Coke, things like that. Really, they're actually pretty acidic. If you look at a can of Coke, right, ingredients are listed by the amounts that are present. So the number 1 ingredient on a can of Coke is water. Number 2 is sugar. Number 3 is like caramel coloring or something like that. 4th ingredient on there is phosphoric acid. Right, it's a weak acid. It's not one of the strong ones. It's a weak acid, but yeah, it's definitely going to lower the pH of that stuff. All right, that's why you should rinse your mouth out after like drinking some Coke so it doesn't eat your teeth. Stuff like that. So yeah, right, here we go. Cool. Let's get into the other P scale. So pH. I mean, most people have heard of pH, but there's other P things. All right, this P basically tells me just do the negative base 10 log of whatever. So pH was negative base 10 log of H, right? H plus. There's something called POH. It's the negative base 10 log of the OH, the hydroxide. There's PKW, the negative base 10 log of KW. There's something called PKA. It's the negative base 10 log of KA. And PKB, it's the negative base 10 log of KB. And KA and KB are things you're going to learn later in this very chapter. All right, but there's lots of these different things. All right, let's keep on rocking. We got more cool stuff to see. All right, hydronium times hydroxide is Kw, which is 1 times 10 to the minus 14. If I do the negative log of all of this, right, the negative log of this equals this. It's like, it becomes plus. It's a property of logs, right? So the negative log of hydronium concentration times hydroxide concentration becomes the negative log of H3O plus the negative log of hydroxide. The negative log of Kw is 14. But what is this? This is the pH. What is this? This is POH. So in other words, pH plus POH equals 14. This is a really handy dandy easy equation, right? If you know the pH and you want the POH, just subtract it from 14. If you know the POH and you want the pH, you subtract it from 14. You kind of do the same thing either whichever one you have, you're going to subtract it from 14 to get the other one. That's what I'm trying to say. Here we go. And so here's like the full figure I had on the other one, right? So you can see the pH and the pH are always add up to 14 as you go through these things. In some alternate universe, they probably use POH to talk about acid or base. Like we use pH, but we could have just as easily been using POH. Like if the coin had landed the other way, who knows? There's something I call the rectangle of doom. I always draw it on the board in class, and lo and behold, it's all over the internet. I didn't invent the thing. I saw it in class at some point, but it's all over the internet. And so I was like, hey, sweet. I don't have to like try to draw this into PowerPoint. I just went and kind of stole one of them. Looks like this. If you have any one of these corners, you have the other three. So if you have the H plus, you can calculate the pH or POH or OH minus of that solution. Really easy. It's just kind of running through this thing, right? If you have the H plus and you want the OH minus concentration. So if I have the hydronium ion concentration and I have this, these are related by Kw. I just take Kw divided by H plus, it gives me hydroxide. If I have hydroxide and I want hydronium, I take Kw divided by hydroxide, gives me hydronium. If I have the hydronium and I want the pH, I just do the negative log of the hydronium, right? That's the definition of pH. Here's a little backwards thing. There's log, there's something called the anti-log, right? It's 10 to the. So if I have the pH and I want the H plus ion concentration, if I want the hydronium concentration, I do the anti-log of negative pH. So I do 10 to the minus pH will get me this. All right. I've seen people make this horrible mistake, and I can only chalk it up to they're not paying attention in class, but on a test, I saw people like doing 10 minus the pH. That is not how to get this. It's not 10 minus the pH. It's 10 to the negative pH. It's exponential up here. So 10 to the negative pH will give you this. Down here, pH and POH, 14, right? So if you have the pH, just subtract that from 14, it gives you POH. If you have POH, subtract that from 14, gives you pH. And over on this side, right, if you have hydroxide concentration and you want the POH, you just do the negative log of the hydroxide concentration. And then going the other way, right, flipping around the other way here, if we have the POH and we want the hydroxide, we do 10 to the minus POH to get the hydroxide. So you don't have to write it this way, but this is just kind of cool to see how everything's connected. If you have any one of these things, you can get the other ones. And your choice of how you get there, it's up to you. So if I give you the pH and I ask you what is the hydroxide ion concentration, there's a couple different ways you could go to get there. It just depends on what you like to do in your calculations. All right, that's it for this section. I will catch you in the next one.